Hi, I'm Juliet.
And I'm Dana.
Today we're going to walk you through how to do problem 7 on homework 8.
We're looking for V out or V naught on this circuit. Okay, so when you first look at the circuit, you're going to want to evaluate what kind of elements you're dealing with. First, we have a node designated as ground, a 10-volt voltage source, and 5 resistors, as well as an operational amplifier. The resistors are all 1 kilo ohm. So this op-amp makes things a little tricky. So before we start solving, let's review some basics.
First off is Ohm's law. This law relates the current going through a resistor to its voltage. George Ohm showed that the voltage required to drive a current through a resistor is directly proportional to the resistance and current. To describe this fact, we use the equation voltage equals current times resistance.
Next, let's talk about Kirchhoff's current law, aka KCL. This law states that the sum of the currents entering the node will always equal the sum of the currents exiting the node. Let's look at this node as an example. We have one current entering and two leaving. Because of KCL, we know that IA plus IB minus I is equal to 0.
Now I want to talk a little bit about the big and scary operational amplifier, also known as an op-amp. Op-amps are active elements in that they supply energy to the system. Op-amps have 6 main parts: an inverting voltage and current, denoted as Vn and In, a non-inverting voltage and current, which you call Vp and Ip, and an output voltage and current, known as Vout and Iout. The inverting voltage and current are associated with the negative terminal, while the non-inverting is associated with the positive terminal. We're only going to deal with ideal op-amps in this class, in which Vp always equals Vn, and Ip and In both always equal 0.
Now that we have some basic knowledge, let's look back at our circuit and try and fill in what we know. Let's look at the op-amp first. Since this is the positive terminal, we know that this node represents Vp, and this current represents Ip, which is equal to 0. Since this is the negative terminal, we know that this node represents Vn, and this current represents In, which equals 0 as well. Also, looking at the Vp node, we see that it's connected to ground. Therefore, Vp must equal 0, and since this is an ideal op-amp, Vn must also equal 0. Now we know a little more information, but we still haven't found the output voltage. Since we have a lot of resistors, I think we're going to need to use one of our strategies for solving circuits.
That's right, Dana. I think we should use node voltage method, aka NVM. Let's take a second to remember what that is. NVM is a way to analyze a circuit by utilizing KCL. There are 5 steps to this method. First, you need to find all nodes in a circuit. Second, you need to designate a reference node. Third, you need to give all other nodes a unique name. Fourth, at each node, you need to write a KCL equation in terms of the node voltages. And last, you need to solve the equations.
Thanks for the refresher, Juliet. Let's look back at our circuit. So the first step of NVM is to find all the nodes. I see a node here, 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 and here.
Next, we need to pick a reference node. Let's make our lives easy and pick the node that we know is at ground to be our reference.
Awesome! I'm going to go ahead and name the other nodes. Let's pick easy names to figure out. How about Vn, V1, and V2?
Perfect. Now let's write some equations. I'm going to start at Vn. To write NVM equations, you pretend like every current is leaving the node. So here we have 3 currents leaving Vn. To find this first current, we're going to utilize Ohm's law. We know that the voltage across the resistor is V equals IR. We know that the resistance is 1 kilo ohm, and we know that the voltage across it should be Vn minus 10 minus 0. If we rearrange this equation, we know that the current leaving the node here is equal to Vn minus 10 divided by 1 kilo ohm. If we use this same process for this current, we'll get the next term in our equation to be Vn minus V1 divided by 1 kilo ohm. We know that this current is going to be In, so we'll just stick that in and we have our first equation.
Awesome! I'll do the next one. Looking at V1, we know the first exiting current goes through this resistor, so the first term will be V1 minus Vn divided by 1 kilo ohm. The next current goes through this resistor, so the term will be Vn minus 0, because it's connected to ground, divided by 1 kilo ohm. The last term will be V1 minus V2 divided by 1 kilo ohm.
For this last node, it looks like we're going to have an unknown current, so let's solve those two equations and see where that gets us. First, let's plug in what we know. Vn equals Vp, which equals 0, so this equation simplifies to this.
So we got V1 to equal negative 10, and if we plug that in for V1 and 0 for Vn in the second equation and simplify, we get that V2 equals negative 30 volts. Because V2 is connected to ground by the resistor that we are looking for the voltage at, we know that V0 is also negative 30 volts.
Great job, Dana! That's how you solve a circuit with op amps and NVM. Thanks for watching.
Bye-bye!